spacecraft operating in the inner solar system usually rely on the use of photovoltaic solar panels to derive electricity from sunlight. In the outer solar system, where the sunlight is too weak to produce sufficient power, radioisotope thermoelectric generators are used as a power source. History: the first spacecraft to use solar panels was the Vanguard 1 satellite, launched by the U.S. in 1958. This was largely because of the influence of Dr. Hans Ziegler, who can be regarded as the father of spacecraft solar power. Uses: solar panels on spacecraft supply power for two main uses: power to run the sensors, active heating, cooling and telemetry. Power for spacecraft propulsion, electric propulsion, sometimes called solar electric propulsion. For both uses, a key figure of merit of the solar panels is the specific power, which indicates on a relative basis how much power one array will generate for a given launch mass relative to another. Another key metric is stowed packing efficiency, which indicates how easily the array will fit into a launch vehicle. Yet another key metric is cost. To increase the specific power, typical solar panels on spacecraft use close-packed solar cell rectangles that cover nearly 100% of the sun-visible area of the solar panels, rather than the solar wafer circles which, even though close-packed, cover about 90% of the sun-visible area of typical solar panels on Earth. However, some solar panels on spacecraft have solar cells that cover only 30% of the sun-visible area. Implementation: solar panels need to have a lot of surface area that can be pointed towards the sun as the spacecraft moves. More exposed surface area means more electricity can be converted from light energy from the sun. Since spacecraft have to be small, this limits the amount of power that can be produced. All electrical circuits generate waste heat. In addition, solar arrays act as optical and thermal as well as electrical collectors. Heat must be radiated from their surfaces. High-power spacecraft may have solar arrays that compete with the active payload itself for thermal dissipation. The innermost panel of arrays may be blank to reduce the overlap of views to space. Such spacecraft include the higher-power communications satellites and Venus Express. Not high-powered but closer to the Sun, spacecraft are built so that the solar panels can be pivoted as the spacecraft moves. Thus, they can always stay in the direct path of the light rays no matter how the spacecraft is pointed. Spacecraft are usually designed with solar panels that can always be pointed at the Sun, even as the rest of the body of the spacecraft moves around, much as a tank turret can be aimed independently of where the tank is going. A tracking mechanism is often incorporated into the solar arrays to keep the array pointed towards the Sun. Sometimes, satellite operators purposefully orient the solar panels to off-point, or out of direct alignment from the Sun. This happens if the batteries are completely charged and the amount of electricity needed is lower than the amount of electricity made. Off-pointing is also sometimes used on the International Space Station for orbital drag reduction. Types of solar cells typically used: gallium arsenide-based solar cells are typically favored over crystalline silicon in industry, because they have a higher efficiency. The most efficient solar cells currently in production are multi-junction photovoltaic cells. These use a combination of several layers of both gallium arsenide and silicon to capture the largest spectrum of light possible. Leading-edge multi-junction cells are capable of exceeding 40% efficiency under ideal conditions. Spacecraft that have used solar power, to date, solar power, other than for propulsion, has been practical for spacecraft operating no farther from the Sun than the orbit of Jupiter. For example, Juno, Magellan, Mars Global Surveyor, and Mars Observer used solar power, as does the Earth orbiting Hubble Space Telescope. The Rosetta space probe, launched March 2, 2004, will use solar panels as far as the orbit of Jupiter. Previously, the furthest use was the Stardust spacecraft at 2AU. Solar power for propulsion was also used on the European lunar mission SMART 1 with a Hall effect thruster. The Juno mission is the first mission to Jupiter to use solar panels instead of the traditional RTGs that are used by previous outer solar system missions. It has 60 square meters of panels. Another spacecraft of interest is Dawn, which went into orbit around 4 Vesta in 2011. It is using ion thrusters to get to Ceres. The potential for solar-powered spacecraft beyond Jupiter has been studied. Power available: in 2005 rigid panel stretched lens arrays were producing 7 kilowatts per wing. Solar arrays producing 300 watts per kilogram and 300 with mass squared from the Sun's 1366 with mass squared power near the Earth are available. ENTEC Incorporated hopes to develop 100 kilowatts panels by 2010 and 1 MW panels by 2015. Deadlink. Future uses: for future missions, it is desirable to reduce solar array mass, and to increase the power generated per unit area. This will reduce overall spacecraft mass, and may make the operation of solar-powered spacecraft feasible at larger distances from the Sun. Solar array mass could be reduced with thin-film photovoltaic cells, flexible blanket substrates, and composite support structures. Solar array efficiency could be improved by using new photovoltaic cell materials and solar concentrators that intensify the incident sunlight. Photovoltaic concentrator solar arrays for primary spacecraft power are devices which intensify the sunlight on the photovoltaics. This design uses a flat lens, called a Fresnel lens, which takes a large area of sunlight and concentrates it onto a smaller spot. The same principle is used to start fires with a magnifying glass on a sunny day. Solar concentrators put one of these lenses over every solar cell. This focuses light from the large concentrator area down to the smaller cell area. This allows the quantity of expensive solar cells to be reduced by the amount of concentration. Concentrators work best when there is a single source of light and the concentrator can be pointed right at it. This is ideal in space, where the Sun is a single light source. Solar cells are the most expensive part of solar arrays, and arrays are often a very expensive part of the spacecraft. This technology may allow costs to be cut significantly due to the utilization of less material. Gallery. See also: Space solar power, solar cells, photovoltaic arrays, for solar arrays on the International Space Station, CISS solar arrays or electrical system of the International Space Station, nuclear power in space. References